Hello, welcome to this NRPy tutorial on how to parse the BSSN equations and Cartesian coordinates. So the goal of this tutorial is to show you how we take the BSSN equations from LaTeX and convert them to SymPy, which is a computer algebra package in Python that NRPy uses as a backend. So you see the equations here in the covariant formulation. Now, you do not have to know anything about these equations. We're simply tackling this from the approach of here's a set of tensorial equations that obey Einstein notation, have stuff like covariant derivatives in them and metrics, etc. And how do we get them in a form that we can manipulate in Python? Specifically, again, using SymPy. So, this first cell is going to import the same equations but handwritten in NRPy, and we're going to use those as a validation test. The notebook is organized in a very pedagogical way wherein we're going to attempt to parse each equation, receive a parse error or a tensor error, debug that error, parse it again, and continue doing that until we have a validated equation. Now, this notebook is fairly long, so I'm going to move through it very fast. It's probably a good idea for you to read through the entire notebook on your own, see what you understand, what you don't understand, come back, feel free to watch the whole video, or there'll be timestamps in the description that will allow you to jump to specific equations if maybe you understand one but you're confused on something in another. Also, several times throughout this notebook, I will have remarks. Now, remarks usually aren't relevant to parsing something in this notebook, but they maybe tell you something about a macro or how to parse a particular edge case that may end up being useful in the future after you finish this tutorial. So I will still make mention of them as I move through. So here's the first equation, which is gamma bar right-hand side. You see it pasted up there. So yeah, let's get started. I just parse the equation and we receive an error message, and that's how we're going to start. Something to note, I'm going to use this parse LaTeX cell magic, which is included in the LaTeX parser package, and the reason for that is it renders stuff beautifully in the Jupyter environment. So inside this notebook, if the equation parses correctly, we'll see the render tech. If it doesn't, we'll receive an error message, but we won't have a stack trace. So it keeps everything nice and compact. So the error message is undefined tensor gamma bar dd. So we need to define that. That tensor is a metric and is defined as h plus gamma hat, where h is the deviation from the flat 3D Cartesian metric, which is what gamma hat is, another metric. That metric we're going to define as the 3D Kronecker delta. So we have three macros to introduce. So macros allow you to communicate with the parser the meaning of the LaTeX that you're trying to parse. And macros are written inside the LaTeX as comments, so they won't be rendered in a tech document or a Jupyter notebook. So vardef is the first macro. It does what you think, it defines a variable, and that can include a derivative option, a symmetry option, several other options that will be useful for this tutorial. But those are the two big ones. The assign macro allows you to assign a vardef option to an already existing variable in the namespace. That's useful if you define a variable just by typing in the equation. Like if I said x equals y and that I wanted to assign a property to x, since x wasn't created using vardef, I can use the assign macro. The parse macro will parse an equation without rendering that equation in a tech document or a Jupyter notebook, because again, these are all just LaTeX comments. But even though it won't render the parser, we'll know what to do with that. The first option to go over here is the metric option, which is for vardef or assign, and it can assign the symmetry sim01, which means that the first two indices are symmetric. It assigns that to whatever tensor you're declaring a metric or labeling a metric, and it will automatically generate the metric inverse and determinant for you. So the parser can generate several things. That is the metric inverse and determinant, covariant derivatives, Lie derivatives with respect to a certain tensor weight, and it can automatically raise and lower indices on tensors using the metric. So anytime you can take advantage of that, it is highly recommended that you do. So in this first example, we need to first declare gamma hat. And so we do that by declaring the Kronecker delta using the cron option, as you see here. We do that with the vardef macro. Then we're going to parse that equation that I mentioned above here, which is that gamma hat equals the Kronecker delta. We do that with the parse macro because we don't want it rendered. And then we're going to assign two options here. We're going to label gamma hat a metric. We're also going to assign it a symbolic derivative type, which means when you take the derivative, it is done symbolically using SymPy. Okay, we have our first remark here, and it's that if you're going to assign a derivative option to a metric, and you want that to apply also to the inverse and determinant, in which case we do, then that option should precede metric. As you see it does here, it comes on the left-hand side of that. In any other case, you can always permute the vardef options, but for this particular case, you cannot. Moreover, you need not define a scalar quantity. However, if you need to assign a property or an option to a scalar quantity, you can use either the vardef or the assign macro. It doesn't matter because, again, it doesn't need to be defined. So you can just use the assign macro if you wish. So if I have a scalar, I could just put it in the equation. It'll be inserted into the namespace. I'll have access to it later. However, maybe I want that scalar to be differentiated numerically because the default diff type is symbolic, in fact. Then I should assign that option to the scalar. Now, something to note about derivative priorities, because again, I said symbolic is the default, so you may ask, okay, why did I waste time assigning it? Because gamma bar has gamma hat on the right-hand side. And when I take a derivative of gamma bar, which isn't going to be symbolic, we're going to define that numerically because it's going to be finite differenced later. Then the parser needs to know that gamma hat has a higher priority, meaning that it needs to be done symbolically, which takes higher priority. So if you physically assign it, then that has higher priority than the default, which is lower than assigning it. Okay, so moving on to gamma bar. First thing we're going to do, we're going to define the deviation, which is symmetric because the metric is symmetric. And we're going to give it a diff type dd, which is the NRPy syntax for, it's a numeric symbol for a derivative, and that'll be finite differenced. So that's actually a suffix that will go on the dd, so it'll become htd underscore dd. We're going to parse the gamma bar equation and then assign the metric option again. Okay, so we paste those 6 lines of code here, parse it again, receive another error message, undefined tensor beta u. Now, you may think to yourself, okay, we're just going to define beta u, which is a vector, using the vardef macro. However, this is the first case where we're going to be renaming a variable, which means that the SymPy name is going to differ from the name that we used in the LaTeX. To do that, or achieve that, we're going to use the srepl macro, which is a macro that does string replacement. But before I talk about that, I want to remark on something. If you're going to require a variable name that is longer than one Latin or Greek letter, you need to surround that variable name in the text command. And as highlighted here, vet, which is what we're renaming beta to, is 3 Latin letters, so it needs to go inside the text command. That basically allows you to build a compound symbol internally within the parser. Okay, so srepl does string replacement given the assumption that string A and string B are considered equal whenever they're equivalent syntactically. So what does that mean? I have 2 examples here of 2 tensor products between S and T. One has a bunch of spaces and one does not. However, if you were to go through them token by token, they're exactly the same because white space doesn't matter. I have a letter followed by an underscore, followed by a left brace, followed by another letter, etc., etc. Therefore, they're equivalent. If you want to test this yourself, I provided a little code snippet where you could take a string in Python A and a string B, run this code here after importing the parser, and it will tell you whether or not the srepl will treat these 2 things as equivalent. Now, the 2 lines here are the lines we need. First, we use srepl to rename beta to vet, and then we define vet and give it a numeric derivative type. And I just paste that down here. We run it, and we get another error message. Now we'll head down to that in a second. I want to mention real quick, there is a persist option, which is the only option for srepl, and what that does is it applies the replacement rule to every subsequent input to the parse function. Why is that useful? Well, again, I mentioned that several things are generated internally for you, and when those are done, parse is recursively called. So for example, maybe you need to do a replacement inside of the covariant derivative, or the right-hand side of one of the covariant derivatives. If you apply the persist option to the sRepl macro, then that will happen recursively. Okay, last thing, remark, the sRepl macro will not replace text inside of a future sRepl or ignore macro. We'll talk about the ignore macro a little bit more later on. And we'll show an example of this. But basically all that means is I have, this string, replace that with this string. sRepls won't do the replacements inside of here. So it only happens to everything outside of the sRepl macros. Okay. And there'll be an example of that later on to make that a little bit more clear what I'm saying, if that seems a bit abstract right now. Okay, so we run this again. It sees another tensor that it doesn't recognize, a bar ud. Now, this is a unique case wherein I could just, again, define that tensor and move on, and it would work. However, I mentioned that the parser can automatically raise and lower indices. So by convention, we're just going to define the down-down version first. But we're also going to rename that to ADD, which is the name that we use in SymPy, and it differs from the LaTeX representation again. So here we go. We do that renaming using the sRepl macro. Then we're going to define ADD, which is symmetric in the first two indices, using the vardef macro. And then we have to assign a metric to it. If you assign the metric gamma bar, it will internally generate this equation you see right here to raise the first index. And all of a sudden, you have access to a bar ud, which is the missing variable. Now, a remark about this. You may think to yourself, why do I have to assign this metric? Well, you don't. There is a default metric for all of these, and that metric is associated with the diacritic. Now, a bar has the bar diacritic, and therefore it would automatically be associated with the metric you declared, which was gamma bar. However, we renamed it, and by renaming it to ADD, we've stripped out the diacritic. So we have to manually assign it. But otherwise, you probably wouldn't have to. And just to mention, it could be the lack thereof a diacritic. No diacritic also has a no diacritic metric. Okay, moving on, we paste those lines in, run it again, unbalanced free index t in the equation. Now the reason for that is we take a partial derivative with respect to t on the left-hand side. However, we were going to rename that. Unbalanced just means that there's no index t appearing on the right-hand side, because there shouldn't be. So we replace that derivative on the left-hand side with the variable name h right-hand side. We're going to do that again using the sRepl macro, which you see done right here. Now, I just want to remark on something because this t indexing is unique. Again, the tensor error happened because that t didn't appear on the right-hand side. However, in the next cell, I'm going to show you how to define a basis, which just means you're going to tell it how to specify your coordinate system, which has to be done when you differentiate things symbolically, which we do for gamma hat, if you remember. So if I defined a basis, such as this right here, txyz, which is 4D Cartesian basis, then t would be the first basis element. So that means that if I were to index, say, gamma bar dd, and I use t as I do here, then that would just replace t with 0, which would mean that this left-hand side just gets the first component. Right, so hopefully that makes sense, but we support numeric indexing if you want to call it that, but you can alias the numeric indexing with the basis, which I guess is probably a better way to put it. Okay. So coming further down here, again, put that in there, run it, can't differentiate without a basis, which I just said. So we're going to define a basis, which we're going to use this here. We have to introduce a new macro. This one is keydef. It's just like vardef, but it's used to define a keyword. In this case, we're going to define a basis. So we just put an XYZ. It's also useful for other things like defining an index range using looping and summation, but you could read that in the documentation. It's more of an advanced feature, but basically, I, for example, is a Latin indice that sums over 0, 1, 2. So it only goes 3D because that's the assumption in GR. So you're allowed to override that type of behavior. Okay. So define the basis, run it again, it parses. However, if we validate it against NRPy, the assertion fails. So this is where it gets interesting because all you need to know up to this point is you got it parsing. Perfect. To fix this validation test, you have to know a little bit about BSSN and the way it's coded up in NRPy. So this isn't necessarily important if you were going through it, trying to get it parsing and to use it in SymPy, but it's still useful to pay attention to this part because it's going to show off features of the parser that you may use while parsing your own LaTeX equations. So the problem here, and the reason this assertion failed, is because every time we see this pattern where we contract beta in a partial derivative, we want to upwind that derivative. So to enforce that, there is a bracketed term, which you'll see here. It's this first bracketed term, and this pattern happens on the first term. We have beta k contracted with partial k. So I have to use this thing called the vphantom command, which you can just treat it like an inline comment because it won't be rendered in the tech, but it's useful for the parser. And we change dd to d up d, and that will tell it that the following partial derivative needs to be upwinded. So you can dynamically change derivative types using the vphantom command. Now, something to note, and this is more advanced, so we don't have to do it, but I'll mention it anyway. This bracketed term is the Lie derivative of gamma bar with respect to beta. Now, I've pasted that in here for all the equations we're going to go through today so that I could show putting in the vphantom command. However, if you wanted to compact that and just use the symbol right here, which is for the Lie derivative, you could just put that in there instead of the bracketed term and allow the parser to automatically generate the Lie derivative for you. However, that means you have to use srepl to replace that pattern with the upwinded version, which again happens recursively at a lower level because the derivative is generated for you. So it's not the way I do it in this tutorial, but I'm just going to mention how to do it because it could be useful in future projects. So what we do is we turn on the persist option again so that it happens at a lower level, and the srepl supports capture group syntax. So the syntax for a capture group is angle brackets and then you number all of the capture groups. So here we have 1 and 1, which means it's going to capture the same token there, and they need to be the same. And then we just paste that over here, put vphantom in the middle, and that's it. It will do that pattern replacement recursively to the Lie derivative. The last thing here is we're going to simplify the calculation of this contraction of the covariant derivative with beta by using this formula in terms of the determinant of gamma hat. And so you see that right here. Something to note, I've used 2 comments, and that's because if I do that double % symbol, that's actually a comment for the parser. It will still be a comment in the tech, and it will be a comment in the parser, meaning that the parser will ignore the entire line until it hits a line break. It's useful for labeling some of your config lines and stuff like that, organizing your LaTeX inside the parser. Okay, so we insert that stuff, parse again, and then we validate, and everything passes. First equation done. So moving on to the second equation, we have this phi right-hand side one. So we paste that in here, parse that. We get unbalanced free index t. So just like before, we're just going to rename the left-hand side. This one's a little bit more unique because we're going to replace phi with something called the conformal factor, which is defined as the exponential function of -2 phi. And we also need to replace every derivative. Now, the exponential of -2 phi will never occur in the equations that you see below, but that of -4 phi will. So I'm going to replace that with the conformal factor squared. So that's our first srepl. The third srepl here is, if you take a look at this, this is the derivation just using the chain rule to replace the partial derivative of phi with the partial derivative of the conformal factor, which we do here. We use the capture group because we want to capture the index that you're taking the partial derivative with respect to and just keep that. And we put on persist because this partial derivative will occur inside of the covariant derivative, which we also need to replace. If I take the covariant derivative of phi, we need that to be in terms of the conformal factor. So we put on the persist mode so that that happens again recursively. And the second equation is to rename the left-hand side. And the way we do that is we replace partial t phi with the version of the covariant, or of the conformal factor, sorry, and then you move this factor of -1/2w over to the other side, which you see right here. And again, we use a more advanced capture group here where I put this ellipsis, and that means continue capturing tokens until you see the next token, which is a line break. So in this case, it's going to capture the entire right-hand side of this partial t-phi equation, and it's going to paste it here inside of parentheses. So putting those equation or those config lines down here, run it again, it parses, fails the assertion error. Just like before, we need to upwind that pattern in the bracketed terms, so we go ahead and do that. And then lastly, we're going to rename k to trace of k, which is the variable that we used inside the NRPy, the handwritten version that we're validating against. So after those two replacements, which you see here, we go ahead and run it again. It parses past the validation test. So second equation done. Moving on to the third equation. We attempt to parse it. So here's an interesting ambiguity that occurs in the parser in that I'm squaring k. The problem is that could be interpreted as the third index of the vector ku, right? I don't know. So the way to resolve that ambiguity is surround the exponent in double curly braces. That will render fine in TeX, and it will tell the parser that this is supposed to be squared. So I make that change, parse it again, unbalanced free index, just like before. We're going to rename it to trace k right-hand side using the srepl macro. So put that in there, parse it, it parses, but it fails the assertion test again. So now we have to, again, enforce upwinding. That's the fix. And then finally, we need to assign the property of this numeric derivative to 3 scalars, which again I can do using the assign macro or the vardef macro, and that's the conformal factor, trace k, and alpha. Because derivatives of those are taken, and they were being done symbolically by default, but now we need to have them done numerically so they can be finite differenced, or computed using finite difference. So we make those changes, run it again, parses, passes the assertion test, third equation done. Okay, moving on to the next equation. We have partial t of gamma, or lambda, sorry. So we paste that in here, attempt to parse it, and cannot index undefined tensor lambda bar u. So we're going to rename lambda bar u to lambda u using the srepl macro, and then we're going to define that variable using the vardef macro. Very similar procedure that we saw before. Here it is. Paste that in here, parse it, undefined tensor delta u. Now, delta u is defined as the difference of the Christoffel symbols, which are generated for you, which you could assume because it generates the covariant derivative. So yeah, the Christoffel symbols are generated for you, so this is just defined as the difference of those. We don't want it rendered, so we use the parse macro. We put that equation in there. And then delta u is just the contraction. Or, yeah, it's just a contraction with the metric. Okay. So we put those 2 lines in there, parse it, run it again, unbalanced free index t, same thing as before. We're going to rename that left-hand side to lambda bar right-hand side using the srepl macro. Paste that in there, parse it again. Now, we used this formatting command qquad to split the equation into 2 lines and then tab out the second line. But the parser doesn't know what that command is, right? So to fix that problem, we have to tell it to ignore that command or remove it internally. The way we do that is we use the ignore macro, which again removes a LaTeX command or a substring, and it's equivalent to doing srepl of, say, qquad to an empty string. So here's the command. It's very simple. Just tell it to ignore that formatting command, parse it again, and we get a little bit of a confusing error, unsupported operator minus. The reason for this is, if I scroll to the right, before the qquad, we have a line break. You cannot break equations into 2 parts like that, which I mentioned down here in the remark. Can't split across a line break. So what we're going to do, it's a little bit of a unique solution, is we're going to add a % symbol, which is just a LaTeX comment, onto the end of that, and then tell the parser to ignore it. So in LaTeX, the line break will still be there, but inside the parser, it won't be. So if I do that, run it again, it parses. Fails the assertion, same thing as before. We have to upwind the bracketed term, paste that back in there, and boom, assertion passed, or validated. So that's equation 4 done. Moving on to the final one, which is equation 5, a little thing that needs to be mentioned here. It has this whole term with this TF, and that means that that needs to be the trace-free of everything inside. Also, on this one term, which you see right here, I have this notation that means I'm going to symmetrize that tensor. And neither of those notations are currently supported in the parser, so you need to manually expand them. So here's the formula to expand this symmetric tensor. And then I'm going to assign everything inside those curly braces to just some tensor called x. And then x hat is going to be the trace-free version, which uses this formula you see right here. So expanding everything out, this is what partial t of a bar looks like. And that's what we're going to be using inside the parser. Okay. Pasting that here, parsing it, first error, doesn't know what r bar dd is. So we define that using the vardef macro, and it is symmetric in the first two indices. Okay, moving on. I should mention that later, way at the bottom of this notebook, we actually compute r bar dd, which is the conformal Ricci tensor, but we don't do it here because the version we're validating against also doesn't compute it. It just leaves it as a symbol, and that's to speed up the validation tests. Okay, so parse it again, unbalanced free index, same thing as before. We're going to rename the left-hand side to a right-hand side using the srepl macro. Paste that in here, parse it, validate it, assertion failed. We need to upwind again. We upwind the bracketed term, and everything passes. And so now we're done. So that's all the BSSN time evolution equations. Now, here are the gauge evolution equations. I'm just going to briefly describe what happens, but I'm not going to go into detail. So if I go down here, it starts, let's see here. Right here, it's these lines. So we rename the left-hand side on the first one. We rename the left-hand side on the second one and on the third one. Now for the second one, I have to rename b to bet and then declare that variable. And on the third one, I have to define a constant eta. Constants will just be pulled out of derivatives, obviously, and you use this const option on the vardef macro to assign that. And then, of course, we have to upwind all of these bracketed terms. And then it parses all three validation tests. Moving on to the constraint equations. Here we have the Hamiltonian constraint and the momentum constraint. So coming down here, for the Hamiltonian constraint, first thing we need is the variable r bar, which is just a contraction of the Ricci tensor. And then we use this operator, which I'll show you here. I'll highlight it. It's hard to see, I know, but it's d squared. And d squared is just the contraction of d bar with itself. And so you can use srepl to kind of define custom operators. So we're going to replace d squared with its expanded version as that contraction. And then the last thing is we're just renaming the left-hand side to h. And so I wanted to do a catch-all, so I didn't have to put two srepls for mathcal_h and mathcal_m. So we use the capture group syntax to just rename it as whatever's inside the curly braces, which is h and m in this case. And then the momentum constraint actually requires no modification at this point. And then finally, we're just going to parse the Ricci tensor, which is quite big. And it also had some of those symmetrized tensors that are expanded. And so here's the full expanded version down here. And it parses and passes the validation test. I guess I forgot to include in this notebook the validation tests of the momentum and Hamiltonian constraint, but it will be included when you look through the notebook online. It's just not for the video. I'll add it right now. But rest assured, they both passed the validation tests. So that's the entire tutorial.